So today in this lecture we will study isomorphisms and homomorphisms of rings. We have seen in a previous video or previous lecture the isomorphism and homomorphisms of groups, and now we will study same things but now for rings. Remember that a group is a set with one binary operation. Now we have a ring which is a set with two binary operation. So for an isomorphism or a homomorphism, it has to preserve both of the two binary operations. We will see. We will start with intuitive approach as we have done for groups. For groups, we defined intuitively isomorphisms by showing that by an example for which we showed that if we have some group and we relabel the elements of that group, and then we will get the other group. I mean the relabeling will be through the tables. So what I am now going to explain is almost a repetition, it is almost the same of what I have explained when we studied isomorphic groups. So we will start with the following example. We will choose this subset S out of Z10. So we have the operation here modulo 10. So this operation here is addition modulo 10, and the operation in this table is multiplication modulo 10. So if we make the addition and multiplication table for the set S alone inside Z10, we will get these tables, the ones you see. For example, 8 times 8 will give us 64, but we will take it modulo 10 and we get 4. Also, 4 times 8 we get 32, modulo 10 we get 2. And here also 8 plus 6 we get 14, modulo 10 it is 4. So these tables represent the addition and multiplications on the set S. So let me remove these things here. So we are working on the set S. Actually we claim that S is a field. S by itself is a field. Z10 is not a field. It has zero divisors. It is not an even integer domain. There are elements that are not units in Z10. For example, 2 is not a unit in Z10. Is not a unit in Z10. So we will claim that S is a field, and the multiplicative identity of this field is 6. Now this looks strange, I know. Try the axioms for S, the set S, with addition modulo 10 and multiplication modulo 10. So if we check the axioms of the field, we will find that gives a field indeed. For instance, 6 is the identity, the multiplicative identity. Is that correct? Watch out for the 6 here. Multiplied by 6 we get 6, by 2 we get 2, by 8 we get 8, by 4 we get 4. From the other side, multiply 6 by 6 we get 6 again, 2 by 6 we get 2, 8 by 6 is 8, 4 by 6 is 4. So 6 here behaves as the identity. Now multiplication is commutative. If you notice that the arrangement of elements here look like a symmetric matrix, that means we have a commutative multiplication. Now, what's about the inverse? What is the inverse of A? It is an element that we multiply by A and get the identity. The identity here is 6. So what element we multiply by 8 we get 6? Let's look for it. It is here. Oh, okay. So in this case, we multiply 8 by 2 and then we get 8 by 2 we get 6. Remember, we work inside Z10. Okay, we don't work with the whole Z10. We took S. We work inside S, but we are working using the addition and multiplication of Z10, module 10. But this is the identity, so we will write 8 inverse equals 2 or 2 inverse equals 8. And check it out for the inverse of 2 is 8. Here we go. The inverse of 4. What is the inverse of 4? 6 is here. It is 4 itself. 4 times 4 is 16. Modulo 10 is 6. And the inverse of 2 is 2 itself. So actually now S is a field indeed. So we will take it as a field. Okay? Now let's go back. Our lesson is about isomorphisms. So what do we want this S for? So we have defined a subset S, which came out to be a field that has 5 elements. What do we want to do with it? We will show it is essentially the same as Z5. S and Z5, we look at them as the same mathematical structure, the same ring. Both of them are rings, both of them are fields. And we are looking at Z5 and S as one field. They have the same structure. Why we look at them as one field? Let's see how we do it. The same as we have done in group theory when we learned about group homomorphisms. We showed that some group is or have the same structure, which means is isomorphic, to some other group if we take the operation table, what was in there an addition, and relabel the names for one group. So take the multiplication table or the addition. Now we will take addition and multiplication tables, rename the elements of the first group on that table, and then you will find the new table that comes out is the table of the other group or the other ring now here. So they have the same structure. That what we mean, they have the same structure, and then we will say that means they are isomorphic. Okay, how do we relabel? Let's denote the elements of Z5 with a bar in here to denote them as equivalent classes or make them distinguished from the elements of S. Remember the elements of S up there were 0, 2, 4, 6, and 8. Okay, now we want to do renaming. We will rename the 0 as 0 bar. The 1 and 6, they will be matched together because the 1 in Z5 is the identity and 6 is the identity in S. Okay, now we relabel 2 bar. We relabel 3 from S by or 3 bar we will be labeled by 8. 3 bar from Z5 will be labeled by 8. 4 bar will be labeled by 4. Okay, now if you see the elements in here that has a slash on them, those were the elements of Z5, okay, in here, and the table inside, there are numbers that have slashes on them. Those were the table addition in Z5. We crossed over the 0 here and relabel it with this 0. Crossed over the 1, relabel it with 6 over 2 bar with 2 over 3 with 8, 4 with 4, as we have done the labels here. That's for addition. Go and do the same thing. Take the table of multiplication inside Z5 and change the labels of the elements in that table to the labels as given here, and the resulting table will be the table of S in both cases, addition and multiplication. Now, if you go back to the tables above there in S, it will be the very same table you get out of these two after relabeling. That means S and Z5 have the same structure. So in here, S and Z5, they have the same ring structure, and we will say they are isomorphic. Okay? So the writing here is just what I have already explained. So they had the same after relabeling elements one by one, and no element is left behind. So I have a one-to-one function and on two between these two sets, and more, I have operations being preserved, the addition and the multiplication. And we will put that on some math. Okay, so let us start it. Again, the relabeling is a function that starts from Z5 and goes to S by saying f of 0 bar is 0. This is the labeling we have done. F of 1 bar is 6, f of 2 bar is 2, f of 3 bar is 8, f of 4 bar is 4. And this function is both injective and surjective, clearly, right? Because S consists of 0, 2, 4, 6, and 8. So clearly, this function is injective and surjective, and it preserves the addition operation. The addition operation is preserved by F, and F also preserves the multiplication operation. And I want to do some demonstration for that, because this is very important. We are defining an isomorphism, and you already know the two properties, injective and surjective. But I will do now a demonstration for preserving the operations addition and multiplication. Now I will demonstrate what do I mean by F preserves addition and F also preserves multiplication. Okay, so let's do that. I will do it in general, not only so I will demonstrate what preserves here means for general groups. I will not work only with S and Z5. So we will assume that we have okay, say, let me use a different color. Say we have a map that goes from group G to another group S, and that map is F. Okay, now assume we have an element in here which is A, and another element somewhere which is let me do it okay here, which is B. Okay, now I will assume that this point here represents the addition of these two elements. I said groups, sorry, I mean rings. So let me avoid using G because we reserved that letter for groups. They are rings. So this is the first operation here, and here the operation between these two elements are, let me denote it plus with a subscript R to denote this is the operation in the ring in the domain. Okay, now what's happening? Let's take the images of each one of these. So I will assume traveling from here to here will give us the image of F, the image of A under F. And the traveling from here to here will give us, oops, I should use red again, no problem. Now, color kind of, I want them to have some indication, maybe. So I will assume this is the image of B. Okay, Now let me use, okay, let me take the image of that one. So it is somewhere, and it is the image of A plus, and the operation is inside of R, A plus B. So I will assume this element somewhere here is the image of that. Okay, now look at it. To reach this element here, we can go two ways. First way, we may go do the operation between A and B inside R, the domain, and then take the image of that operation. So then we got here. Good? Okay. There is another way to reach that point. Take the image of A, so let me do it in this color. Take the image of A, then to do operations inside the ring R. We will do operation inside the ring S. So take the images here. So we got f of A and f of B. Now take the operation f of A plus f of B, but now this plus is the addition of S. Okay? Question. Where is that element now? Is it the same as this one? So if we take operation here, we go that way. Is it or not? If we have an isomorphism or a homomorphism, this is the definition of a homomorphism, then the answer is yes. This is what homomorphism do or does. This is what homomorphism does. So what homomorphism does, it says, okay, if you want to take operation inside the domain of two elements, it is the same as if you take the image of each one of them and go to the range and do the operation there. Okay? So this is the idea of homomorphism. Now we assumed we done this for addition, and I believe I made a demonstration, such a demonstration, when we studied homomorphism or isomorphism for groups. Same thing will be done for addition. Sorry, this is for addition. Same thing will be done for multiplication. So instead of making another graph, you please make that other graph. I will go back and say, oh, okay, same thing if I change addition to multiplication. So this is multiplication. I'm changing here. To the left is multiplication inside the ring R. To the right is multiplication inside the ring S. And this also will be multiplication. So I will write here another rule. If I multiply two images inside the domain, the ring in the domain, if I multiply two elements inside the ring of the domain and then take the image of the resulting, it will be the same if I take the images first and then do the multiplication in the ring, which is in the range or the codomain. This is S. So these two properties, along with injective and surjective, will give us a function which is called an isomorphism. So this function here is injective and it is surjective, and these two properties for this function are satisfied. How do we know that? This is what it means when we have the tables, addition table and multiplication table. When we have these tables here for Z5, these tables for Z5, okay? But when we done the relabeling according to the one-to-one and into function, we produce the tables of S. How this happened? How could this happen? Because the function allows the two properties that I have already done. This is equivalent. The converting of tables after relabeling is originally because of these properties here, the two properties here. Now this motivates us for the following definition. A ring is isomorphic to a ring R is isomorphic to S, and we will write it this way. If we can find a function from R to S which is injective, surjective, and this property here is satisfied. Now there is no R in here and S in here because this shall be automatically understood what operations for what string we use. And here the multiplication is inside R and then multiplication inside S. And the function will be called an isomorphism, and then we will say R is isomorphic to S. R is isomorphic to S. So you can say F distributes over operations. I say F preserves operations. First example on isomorphisms. We have seen the field of 2 by 2 matrices that has this form. So K consists of all 2 by 2 matrices with entries from real numbers, but it is a special form of matrices. This is A, this is A. It can be any real number, and this is B, and this is negative B, any real number also. And we will show that K is isomorphic to the field of complex numbers. And the map that takes K to C is simply take this element in here and make it as the real part of the complex number, and the element that is at that corner multiply it by I, so it is the imaginary part of the complex number. So we will show that F is injective, surjective, and it preserves the two properties that we have already seen. Okay, so to prove it is injective, we will assume that the images of two matrices, this matrix here and this matrix here, are the same. But the image of that matrix is A plus BI, and the image of this matrix is R plus SI. As we see, this is the real part, this is the imaginary part. But now we have two complex numbers that are equal, which means the real parts are equal and the imaginary parts are equal. So these two matrices are equal. So their images are equal because they are the same matrix. So F is injective, 1-to-1. Now to show F is surjective, it is very trivial. The function F, as we said, goes from, so let me show it here. Let's go to the function again. So move please. Okay, where's the function? Okay, so we want to show it is surjective, so we'll take any element from C here. So how elements in C looks like. Oops, let A plus BI belongs to C. Then simply the image of, so choose this A, B, negative B. So we are using the integers that comes inside that complex numbers, and simply this will give us back the complex number we started with. So it is direct or obvious to see F is surjective. Now to show F has enjoys the two properties, preserve the addition and multiplication. It is here already. I made it ready. I wanted to have it ready for quick. Capital A and capital B are in K matrices. We want to show F of their addition is the addition of their images, and the image of their multiplication is the multiplication of their images. This is a good sentence to say. The image of the addition of two elements is the addition of their images, and the image of a multiplication of two elements is equal to the multiplication of their images. The image of multiplication equal multiplication of images. Okay, you may say it that way. Okay, now if we choose two matrices from A, so we will keep this parentheses square. So this is, if we take this A to be A and this is to be B, just add the two matrices, and then this is the addition. Take the image, it is the element in here as the real part, and we take this element as the imaginary part, which means we multiply it by I, and then we can rewrite them as addition of two complex numbers, and this comes out to be the image of this matrix and the image of this matrix. So this is so direct. And same thing for multiplication. Take two elements from K, two matrices of that form. Notice we must have this element here the same as this element here with a minus sign. Now if you multiply the two matrices, you get that. Now take the image, that will be the real part, and this will give the imaginary part multiplied by I, as we have see here. Now, this addition, if you notice, it can be written as multiplication of these two complex numbers, multiplication of them, but this is the image of capital A, and this is the image of capital B, and then we are done. So F is an isomorphism. It preserves addition or distribute over addition and distribute over multiplication. The identity map is always from a ring to itself, which is given by I of r, small r is small r. So we're doing nothing. So easily the addition is the identity is distributed over the addition, and same thing for multiplication. So the identity is always an isomorphism from a ring to itself. Okay, good. Now, what if we have a ring R isomorphic to S? Now the question, can we say S isomorphic to R? What makes R isomorphic to S? Because we have a map going from R to S, which is isomorphism. Okay? As it is isomorphism, that gives F is 1-to-1 and in 2, so it is bijective. And that gives F inverse exists. You know, you can define an inverse for the function when it is 1-to-1. Okay? We don't need on 2 to define inverse. 1-to-1 is enough. But we want to define a function, in this case here, we want to define a function that coming back from the whole S. So the function is going from R to S. So it can be the inverse of that function, F inverse, exists if this is 1-to-1, if this function is 1-to-1 only. But we don't want this only. In this case, we want the function to brings back all of S. So we want the inverse to brings back all of S. I mean, I want the inverse to be defined on every element on S. That's why now I want it to be also surjective, not to guarantee the inverse exists. The inverse may exist without a function being surjective, no problem. But now we want the inverse to exist and be defined in every element in the codomain. Codomain means now it is the range. So F inverse exists. Now F inverse is defined from now, see what I'm writing here, from S to R. Now I can freely write it starts from S. I did not say it starts from the image of S, of F, from some subset inside here. It starts from the whole S. Okay, now the question here, is this an isomorphism? We know since F is 1-to-1 and it is surjective, then F inverse is 1-to-1 and surjective. You should know that in Foundation of Mathematics. But now the question, what if we have, can we have that, the other two properties? Can we have, like, if we have S1 plus S2, would that be the same as F of S1 plus F of S2? Now the plus here is inside S, but the plus here is inside R. Now, I shall add inverse here. And also, is it true that we can distribute this over the multiplication? This is multiplication from S. And S1, S2 are elements. Let me emphasize that. Elements from S, capital S. So this is the multiplication inside S. And the inverse distribute over that multiplication. But now the multiplication is from R. Now, to prove F inverse is also an isomorphism, for this one is also an isomorphism, we need to prove these two properties. Can you do that? And they do happen, yes. And this will be left as an exercise for you to do. Okay? So now we go back. R is isomorphic to S. S is isomorphic to R. If R is isomorphic to S, then S is isomorphic to R. This is a symmetric relation. It is also transitive. If R is isomorphic to S, S isomorphic to H, some other ring, then R is isomorphic to H, and the isomorphism is the composition of the two isomorphisms. The first one between R and S, and the second one between S and h. Now we go to homomorphism. Homomorphism are a special case of isomorphism. It is more general than isomorphisms. Okay. Let me see. Let's see what does that mean. If f is a function from a ring R to a ring S, then it is called a homomorphism. If I require here, or we require here, the distribution over operations. So we do not require injective and surjective. We only want the distribution over the two operations, the ones I just demonstrated using a figure now. So every isomorphism is a homomorphism, but the opposite is not true. So I may write like if this is the domain of all homomorphism, and then isomorphisms will be a subset. So every isomorphism is a homomorphism, but the opposite no. There are some homomorphisms that are not isomorphism, and this is an example of it. Take a function from z to z6 defined by take the a and take an a from the integer and take it to its equivalence class inside z6. For example, f of 13 is the same as equivalence class of 1, right? And this is the same as f of 19. Do you agree? Because the equivalence class of 13 in z6, it is the same as equivalence class in 1. It is the same as equivalence class in 19. So this function is not 1 apparently, right? So this function is not injective. It is surjective, but it is not injective. Okay. Now let's check whether it is a homomorphism or no. So let us take f of a plus b, where this is plus, where a and b are integers. That means we want to take the equivalence class of a plus b. But we have seen this is the same as the equivalence class of a plus the equivalence class of b, and this is f of a plus f of b. And now for abbreviation, we are not writing, for instance, this is the addition inside z6. Now this is the addition inside z6, but this is the regular addition we know. So we are not writing this anymore because you can guess and figure out the addition right away. And same thing for multiplication. If we do the multiplication of two integers and take the equivalence class of that, it is the same as if we take the equivalence class and do the multiplication, but this is the multiplication of images. So f is a homomorphism. So it is a homomorphism, but not an isomorphism. Why? Because it is not injective. It is not injective. Okay. Another example of homomorphism, from the real numbers to the matrices of real numbers. So it will take a real number r. So it will take a real number r and it will send it to 0, 0 minus r minus r. So it uses a number and it makes a 2 by 2 matrix out of it. And this number is the same as in here. So if we add g of r plus g of s, this is g of r, g of s, add them, you get this and you get that so quickly, and this is so clear that this function is a homomorphism. So this is very quick. I will let you look at it. Now the question is it isomorphism? Can somebody answer me? Is it an isomorphism? Is G an isomorphism? Somebody answer me. Shall I wait for an answer if it is yes or no? So J is not surjective. And so J is not isomorphism. The question is no. Okay. What else we have down there? Okay, what's about this function now, from real numbers to real numbers? It is onto, this function is injective. right? How do you know it is injective so quickly? Because it is a line, right? It is a line increasing all the way, so it is 1 to 1. So it is injective, and it is surjective also. But these two properties, like distributing the addition over 3 and 5, is not correct. And I mean the addition or the multiplication is not correct. And that will work for all pairs of numbers, not only 3 and 4. So this function is not an isomorphism. So the examples above there give us homomorphisms that are not 1-to-1 or not surjective, so they are not isomorphisms. But here it gives us a function which is injective and surjective, but it is not a homomorphism, so it is not an isomorphism. Okay. Now, a very important and theorem here. I need a space to prove it. Okay. So I will give the proof so quick, very quick. It's very easy. It says, but let us see what it does. It say. If we have a homomorphism from R to S, then it takes the 0 to 0. Like if you make a graph for it, somewhere I need all that space where we can make here. Just make some graph for you to remember. So it takes the 0. So oops, this is f. This is the function f, which is right here. It is a homomorphism. It takes the 0 of this ring to the 0 of this ring. Now you may ask me, does it take the identity? We will say yes. In part 4 here, it will take the identity, but there is one restriction for it. Let me go for it now. If the ring in the domain has an identity, it must. The question was, does it take the identity to the identity? So we require an identity in R to make that question correct. But also we require f to be surjective. So let me write from here to here. If we have f surjective, if we add one more property, which is f surjective, then the identity of the ring R will be mapped to the identity of the ring S. And I shall replace this here to S, not to R, the 0 of S here. Okay. Now what does this theorem say is also, okay, let's prove this part so quick. How we prove it? We will say, okay, add 0 to 0, the 0 of R inside the function, and because we have a homomorphism, then we can distribute, right? We can distribute. And okay, so what else we do? Okay. Then we can distribute. Okay. Now I want to move this a little while. Okay, I need the space to the left. But going back here now, this was f of 0, right? Because 0 plus 0 is 0. And look what happened here. We have f of 0, and we can say, okay, you know, yes, this is f of 0. So what I get now, look what happened here. F of 0 equals, okay, so equals f of 0 of R equals f of 0 of R plus f of 0 of R. I need the same color here. Okay, now what happened in here? Now I will use equality from here to here. So this, okay, let me write that equality. I got f of 0 of R to equal f of 0 of R plus f of 0 of R. Now what can I do next? I do cancellation, right? Can I add the 0 of S here? Yes, I can, because f of 0 of R is an element inside S, right? If I add it to the 0 of S, then I get f of 0 of R. So what do I need it for? Okay, now we do cancellation, right? Because we learned we can do cancellation for addition or subtraction. We take this off, and then we got that, and then intuitive, but did not come out so quick. Okay, now what's about proving this part here? Let me erase this. I want to benefit from these spaces. So the part 2 says the image of the additive inverse is the additive inverse of the image, right? Can we say it that way? The image of the additive inverse is the additive inverse of the image. Oh, trying to. Okay, the eraser is going very slow. Okay, so let's prove this part here. Okay, let's prove this part here. I want to show that, look at it, the inverse of f of a, the additive inverse, you see that? The additive inverse of f of a is f of negative a. Let me say it that way. So how do I do that? So I will show that f of negative a, if I added 2, I want to show that the inverse of f of a, so I want to add f of a. I want to find the inverse of f of a, so I will show you that f of a being added to f of negative a, then we get 0 of s, right? If that happen, that means the inverse of one of these elements is the other, because we're adding them, we're getting 0, right? So if we can do that, then we are done. So this is the question. But this equals, we're having a homomorphism, f of a plus the additive inverse of a. But this is f of 0, right? The 0 of r. And this is the 0 of s by part 1 here. So we got this true. So the inverse of f of a is f of a inverse. Okay, good. Now let's go and prove part 3. In this space, we want to show that, okay, this is so direct, f of a minus b, we will replace a minus b by a plus the negative b, the additive inverse of b. Now we can distribute f over the addition because we have a homomorphism, right? F of negative b. Now we can replace negative b by f of negative b by negative f of b by part 2. So in here, let me say this is by part 2, and if I come back here, say this was by part 1. So by part 2, we get f of a minus f of b. So part 2 is used to convert this to this. Okay, so we have proved part 3. To prove part 4, okay, what do we need to do? We are assuming R has the identity and F is surjective. We want to prove this is the identity of S. This is the identity of the ring S. That means if I take any element from the ring S and multiply it by this inside the circle, then the result is that element, right? Does not change it. So to prove 4, I will say let small s belong to capital S. Now we will use the surjectivity. Then there exists R inside capital R such that small s equal f of R. Good? Okay. Now what do we want it to show? We want to show a small s multiplied by this element in here will keep small s as it is. So this will be the identity because the small s is an arbitrary of the ring S. So let's see that. S multiplied, now this multiplication is from the capital S by f of 1, the identity of R. It equals f of small r, because S equals f of small r, multiplied by f of the identity of R. But now we have a homomorphism. So that means we can say this is f of 1 multiplied by the identity of R. and this is the operation inside R. But this is f of R, oops, and this is S. So what happened here, S times f of 1 gives S. So that means f of 1 here is the identity. Okay? Now, let's prove part 5. It says if U is a unit in R, then its image in S is also a unit. And it tells us that the inverse of the image, this inverse is not for f. F might not be invertible function. We are not requiring here f to be injective for the whole theorem. All what we need, f is a homomorphism. It could be homomorphism but not injective. We have seen such examples already. So it says the inverse here means it is the inverse of the image of U. It's the inverse of an element, not of f. It says how you obtain it. F of U is in S, and you want its inverse in S. How you obtain it? You take the image of the inverse of U. U is an element of R, and we are assuming it has an inverse in R. We are saying it is a unit. Take the image of that inverse, then you get an element in S. We are saying this element in S is the inverse of f of U. So how to prove this? Okay, let's see. Let's take, actually, let me write to prove this. So I want you to know what we want to do so that the things come clear to you. To prove that, let me square it in green. We want to show that f of U times f of U inverse inside here is the identity of S. Do you agree? So what will happen here, I am saying that I am multiplying this element by that element and then get 1, which means the other element is inverse for the first one, and the opposite. The first one is the inverse of the other. So two elements multiplied by each other, then we get the identity. So each one of them is the inverse of the other. So the inverse of f of U will be this. This is what we are saying. The inverse of f of U is the image of the inverse. So the inverse of the image is the image of the inverse. So this is what we want to show in green, right? So let's do it. Let's start with it. So f of U multiplied by f of U inverse, because we already know U inverse is in R, right? Because this says U inverse, this in here, this says U inverse belongs to R, because we are assuming it's a unit. Now f is a homomorphism, so we can do that. But this is the identity of R, and by part 1 we know this is the identity of S, and then we are done with that. Okay, good. So remember these properties. Homomorphism preserves the 0, takes the 0 to the 0. The image of the inverse, additive inverse, is the additive inverse of the image. If f is surjective and the ring in the domain has an identity, then the identity of the ring in the image, the codomain, is the image of the identity of the ring in the domain. Okay, and the image of a unit is a unit. Okay, good. Now, if we have, as a corollary of the above theorem, it says if we have this a homomorphism, then the image of f is a subring. Oh, very interesting. The image of f, it says image of f is a subring of, the image of f is a subring of S. Like, okay, make everything pictures. Pictures all help you to comprehend the ideas. So if this f goes from here to here, and it is only homomorphism, we are not saying it's surjective or whatever. Okay, and now the image of R, it might be not all of S, it might be a subset of S, which is the image of f or the image of R. So the function will take 2 to this specific. We are saying this set here is subring is not only subset, it is also subring. And why we do so? Why we how confident we are? Why? We will use the above theorem to prove it. We will define f simply, restrict f, not restricting. Take f from R, but not to all of S. Take it to the image of R, where f is defined in here. Or more clearly, I will define an h, which goes from R and goes to the image of f. That will be a better use of notation. Now, what's about this h? It is a homomorphism. Now, h is a homomorphism, and it is also surjective. So prove it. Because h is the same as f, actually. So f of small r equals h of small r. So, and it is surjective because it starts from R and goes the image to the image of R. But write them down. And now H is homomorphism and it is surjective. So by the previous theorem, what we get? By previous theorem, what we get? What does the previous theorem says? Does it say this? Okay, this shall be direct. Okay, homomorphism of Franks. How now? Okay, the images are subring now because why is that is correct now? But that did we take? I want to make an isomorphism actually using the kernel, but we're not supposed to use the kernel for rings up to this point. Oh, okay, so we need to do it by details. Technically, we're not using we will use parts of the theorem. I was planning to use kernel in here, but we did not define kernel yet for homomorphism of rings. So I will prove this in details. Proof. I want to show that let me name it, let H equals the image of F. We want to show H is a subring of S, and I will write subring of S. So let me do it maybe a little quick. What do we need? Okay, what do we need for subring? Do we need to remember last time we need two axioms? If we have two elements in that subset, then we show their subtraction and their addition is in there, right? Subtraction and addition. So let A, B belongs to image of F, which is H. Then okay, I'm giving it too much details. A equals f of R1 and B equals f of R2. Correct? Where R1 and R2. I want to do this. Okay. It belongs to ring R. Okay. Now, A minus B is f of R1 minus R2. So quick. But R1 minus R2 is in R. So this belongs to the image of F. Boom. A times B equals f of R1 times R2. So there are some movements from here to here. We say f of R1 minus f of R2, but f is a homomorphism. Then I do this. So, but now if I will do it for a quick, and this belongs to the image of F. And then we are done. And I named this H and did not use it. So what happened? So let me say AB belongs to H and A times B belongs to H. And this is for every A and B inside H, and that gives H is a subring. Okay. Existence of isomorphisms. You might be asked that given two rings, are they isomorphic or no? And then if they are isomorphic, then they have to share the same structures or same properties. For example, they have to be, if they are finite, then they have to contain the same number of elements. If one of them has an element of order 5, then the other has to have an element of order 5. If one of them has 1 unit or 2 units or some number of elements that are units, then the other must have the same number of elements that are units inside the other ring, assuming these two rings are isomorphic. Therefore, that means if the given two rings have the property, one of them has, say, 3 units and the other has 1 unit, then they are not isomorphic anymore. No way. Okay? They must have the same number of units, for example. They must have the same number of zero divisors. If you give an equation and you find out in that ring there are 2 solutions for this equation, but in that ring there are no solutions, or 1 solution, or 3, not 2 solutions, the same as this one, then they are not isomorphic. So let's look at example and see how this thing works. It says, this example says, I can show you that Z12 is isomorphic. Z12 is isomorphic to Z3 across Z4. Oh, he wants to show us that thing. So he must produce a function which is 1-to-1 onto and distribute over addition and multiplication. So it must produce an isomorphism, right? Okay, so let's see if we have an isomorphism F that takes Z12 to Z3 cross Z4, then it must take the identity to the identity, right? We just proved that homomorphisms does that. Take the identity to the identity. So if F is an isomorphism, then it is a homomorphism. So it does that. So it will take the identity to the identity. Now, 1 is the identity of Z12. 1 is the identity of Z3 cross Z4. Okay? So we must have that f of 1 equals 1, 1. The ordered pair 1, 1. Okay? And see what we get. F of 2 is f of 1 plus 1. But this is f of 1 plus f of 1 because we have a homomorphism. F of 1 is 1 plus 1, 1. So we get to this. Okay, again, f of 3 is f of 2 plus 1. And we know what's f of 2. We already have it. 2 plus 2. And f of 1 is 1 plus 1. And then add, we get 0, 3. Oh, how come? 2 plus 2, comma 2 plus 1, comma 1 gives 0. Yes, because we are working here and the addition or multiplication in the first coordinate is modulo 3 and in the second coordinate is modulo 4, either addition or multiplication. So 3 plus 1, 2 plus 1 here is 3, so we give 0. So again, f of 4 is f of 3 plus 1. And this is f of 3, we got f of 3 in here. This is 1 plus 1, so we get 1, 0. Repeating all that, we get f of 4, f of 5, 6, and f of 7, and all the elements in Z12, all of them. And that defines an isomorphism from Z12 to Z3 cross Z4. But you may say, wait a minute. What you have done is you defined a function which is 1-to-1 and onto. How come it is a homomorphism? It must distribute the addition and multiplication. So we either work the multiplication table of Z12 and relabel the elements of Z12s according to these images here, and then we will produce the multiplication table of Z3 cross Z4. And we do the same thing for addition table again. Or we can get a formula for F and prove that formula achieve these two properties. And here we go. We can define actually, let me rewrite it here. Take an element from Z12 and it is the equivalence class according to module 12 and send it to where? Send it to the first coordinate, but in the first coordinate take the equivalence class of that A modulo 3. in the second coordinate take it modulo 4. Okay, now what we get if we have two elements, f of a plus b modulo 12, what we get? It says we'll take a plus b, but modulo 3, and again in the second coordinate a plus b, but modulo the equivalence class modulo 4. Okay, and that will gives, we can write it this way, equivalence class of a plus equivalence class of b modulo 3, equivalence class of a plus equivalence class of b, but this time modulo 4. But this can be rewritten as the following ordered pairs: equivalence class of 3, equivalence class of 4. This is of a modulo 4 modulo 3, plus equivalence class of a, but this time modulo of b, sorry, modulo 3, plus equivalent class of b modulo 4. Too much writing. And this is f of a, right? This is f of a plus f of b, and then we're done. So again, this part here is f of a, and this part here is f of b. Okay, now same thing can be repeated, but instead of writing addition, we write multiplication, and nothing changed, just the operations. And this will be multiplication, this will be multiplication. So f is an isomorphism. It is 1-to-1 on 2 above as the labels in here. It proves it is 1-to-1 and on 2, and in here it proves that it preserves operations. Okay, now this example says Z4, it has 4 elements. Z2 cross Z2 also have 4 elements, but they are not isomorphic, and there are many reasons for that. In Z4 we have 2 elements that are units, right? 2 elements that are units, 1 and 3. But but there is one element. So let me write that. The book has different reasoning. There are 2 elements in Z4 that are unit. These 2 elements are 1 and 3. Now if you go to Z2 cross Z2, but Z2 cross Z2 has only 1 unit, which is the ordered pair 1 and 1, and the remaining are 0 divisors. Okay, in the book I remember it says if we have a function f from Z4 to Z2 cross Z2, which is say suppose this is an isomorphism, then it must take 1 identity to the identity, right? 1-to-1. Good. And also it must take 0 to 0, which is the 0 in Z2 cross Z2 is 0 0. And it will take f of 2 to f of 1 plus 1, which is f of 1 plus f of 1 again. But this gives, what is f of 1? F of 1 is 1 1 plus 1 1 again. And this gives, we are working in Z2 cross Z2, so we get 0 0 to 2, which is 0 0. Or what we got in here, f of 0 equals 0 0, and we got f of 2 equals 0 0, right? So f never can be injective. So we use the homomorphism property. If, let me say, if it is a homomorphism, then f never can be injective. We used homomorphism property from here to here. So if you assume it is an isomorphism, then it is a homomorphism. Then we use that property, and then we get a contradiction. Now this motivates us for the following. It says, suppose there is an isomorphism between two rings. Isomorphism. It says that if we have element A, B, C with some property, then their images must enjoy the same properties. Whenever this happens, the isomorphism is said to preserve. So these properties are preserved by isomorphism. So isomorphism preserves property. It preserves the whole structure of the two rings. So definitely it will preserve the property of every element. If the element is unit, its image is a unit. If it is a zero divisor, then its image is a zero divisor. If it has order 5, then its image is order 5. If it is a solution for some equation, its image shall be a solution for that equation. Okay? Now this will help us to decide sometimes why some rings are not isomorphic. For instance, okay, so let me, these are the ring here, the zero element, the identity element, the unit properties are being reserved by isomorphism along with the ones I already said. And when we suspect that two rings are not isomorphic, then it is enough to find one property which is not satisfied. I mean, a property in one ring which does not, which is not in the other ring. For instance, let us go to Z8. What do you think? There is a property in Z8 which is not in Z4 cross Z2. They have the same number of elements, right? But what is the property in there? So go and find how many units in there. The units in Z8, you know them, they are 1, 3, 5, and 7. And also, how many units in here? The units are, what are they? I think, okay, they are 1 and 1 only. The units of 4 are 1 and 3, so the first coordinate shall contain 1 and 3. The units of Z2 are only 1. So the second coordinate contains 1 only. And the first coordinate, so the first coordinate contains the units of Z4. The second coordinate contains the unit of Z2. So we have here 4 units, while we have here 2 units. So they are not isomorphic. They are not isomorphic. Same thing here. What do you think? Each of the rational numbers, the field of rational numbers, R or C, is none of them is isomorphic to Z. This is very clear because Z is integer domain. It is not a field, and each one of these is the field, but yet we don't mean that so far. The units in here, what are the units in Z2? We have 1 and -1 only, but in here every element, non-zero element, is a unit. So in each one of these there are infinitely many units, but in Z we have 2. Now you may ask whether Q is isomorphic to R or no. So this is a question. Q is isomorphic to C or no? Real numbers are isomorphic to the complex numbers or no? Think about these questions. Look into the properties we just mentioned. Okay. Again, example, a property of being commutative is preserved by an isomorphism. This might be a good question, like show that if from, or show that two isomorphic image of a commutative ring is commutative. Or if there is an isomorphism from a commutative ring, there cannot be an isomorphism from a commutative ring to a non-commutative ring. Something like that. All of them have the same meaning. Now, if we assume that we have an isomorphism, this is isomorphism, and this ring is commutative, and we want to conclude that this one must be also commutative. Now we have an isomorphism. That means F is surjective, right? Now we want to show S is an isomorphism. So let S1, S is commutative. Let S1, S2 belong to us. We want to show that S1, S2 equals S2, S1. Okay, so that means S1 equals f of R1, because F is an isomorphism, so it is surjective, and S2 equals f of R2 for some R1, R2 inside the ring R. Okay, now S1 times S2 equals f of R1 times f of R2, but we have F isomorphism, so it is f of R1 times R2 inside the ring R, but now R is commutative, so it is f of R2 times R1. But again, F is a homomorphism, so dispute over operation. So we go that way. But this is S2 and this is S1, and went all the way S1, S2 equals S2, S1, and that gives S is commutative. Okay, and that's it for today.